An isolated metal sphere of radius r is charged so that the electrical potential at its surface is given as V naught. On figure 5.1, sketch the variation with distance x from the center of the sphere of the electric potential. Your graph should extend from x equals 0 to x equals 3r. So from here, this is the range that we have for the x-axis. Now on the y-axis, we have potential V, and we know that for a metal sphere, inside the metal sphere, the potential remains a constant maximum, right? And then you move, so this is your sphere, and here you're inside the sphere. This is my r. Now inside this metal sphere, the potential is a fixed value that it's maintained at that fixed value, the surface of this at, so in this case, it is at 1.0 volts, right? Now, as you move away from this, we know that the potential falls off as the inverse square of the distance, which means that starting from r, this point, we'll observe a curve with a decreasing gradient that should pass through this point, right? So it will not really look like this, but it will pass through this point, which is half of V naught at 2r. So it will look something like this, right? Now, this is how we would have a graph for the variation of distance x from the center of the sphere of the electric potential. Part B says photons having wavelength lambda are incident on a metal surface. The maximum wavelength for which there is an emission of electrons is lambda naught. So at lambda naught, we observe emission of electrons when the wavelength hits the metal surface. So this is happening. We have a photon coming in, and it hits the surface. And when it hits the surface, an electron comes out of the surface. And we are saying that when the value for the wavelength is lambda naught, that's when it's capable of putting out an electron. So for the photons of wavelength lambda naught by 2, the maximum kinetic energy of the emitted electrons is EMAX. And so this is for lambda naught by 2. That's when we have the maximum kinetic energy. Sketch the variation with wavelength lambda of the maximum kinetic energy for the values of wavelength between this and this. So here we can see this is lambda naught by 3, and this is the maximum lambda naught. Now we know the kinetic energy of this effect, which is called the photoelectric effect, is given as hc over lambda, where h is the Planck's constant, c is the speed of light or electromagnetic waves, lambda is the wavelength of the photon or the electromagnetic wave which was incident on the metal surface. So if you look at this expression, you immediately see that the quantity, the kinetic energy, and the wavelength are inversely related. So we would expect a negative gradient for our line. Now, we know that at lambda naught by 2, we observe maximum kinetic energy. So immediately we can write down that point, which is this one. And when it is at lambda naught, the kinetic energy is 0. Now, what about when lambda would be 0? So if lambda in this equation goes to 0, then the kinetic energy tends to go towards infinity, which means that you would observe a vertical asymptote at this line at lambda equals to 0, which means that the curve that passes through this thing never touches this axis but goes parallel with that axis, and then it will curve something like this, and then from this point onwards it will be a straight line with a decreasing gradient. That would look something like this. A slight correction over here would be that at lambda naught by 3, we would observe 2 times E maximum according to this expression. So this curve, let me redraw this one, should look something so. This is how it would look like. Here it's going towards infinity, and here it's decreasing gradient curve, and then there at this point, because it's an inverse relation between EK and lambda, so it is just a straight line that's going downwards. A pure sample of radioactive isotope contains N0 nuclei. The half-life of the isotope is T1 by 2. The product of the radioactive decay is stable. The variation with time t of the number n of nuclei of radioactive isotopes is shown. So we see that as time is increasing, the number is moving towards less and less and less values, right? Now, on this figure 5.3, label on the time axis the time t 1.0 times t half and time t 2.0 t half. Now, the half-life means that if you have a total number n, after its half-life, one half-life, it will go towards half of its original value. After one half-life, and after two half-lives, it would go again half of what it's half, so that's n naught by 4. So one half-life is at this point, n naught by 2. So this point on the graph is 1t1 by 2. What about 2t1 by 2? 2t1 by 2 is half of this value, which lies over here, which means that this point is 2t halves. Next, they say sketch the variation with time t of the number of nuclei of the decay product for time t equals 0 to time t equals t. So at t equals 0, we'd have 0. Well, why? Because these are the number of nuclei of the decay product. So at t equals 0, we don't have any decay, right? And at half-life, t half, we have half of it as decayed. So we'd observe a straight line that passes something like this. Okay, so it didn't become a straight line, but it would look something like this. Yeah, so this would be the line that we would observe.